Hello dear students, in this video I am going to give the list of formulae from the chapter Magnetism and Matter. This is the fifth chapter from second PUC physics syllabus. Okay, so this list of formulae will help you for your board examination so much. So first of all we have a bar magnet. So here a bar magnet consists of two poles. One is north pole and the other one is the south pole. So there are magnetic field lines. Look at this, they are represented by B. So they are directed from north pole to south pole. Outside the magnet there will be magnetic field lines from south pole to north pole also inside the magnet. That's why we call magnetic field lines for closed loops. They form closed loops. Okay, so here we have the magnetic length. Actually we consider dipole magnet as a dipole, so whose length we consider it as 2L. It is not the actual length, it is around 80% of the actual length. Total length is L, but the dipole length is around 2L. It has two poles. Okay, it has magnetic dipole moment also represented by small m or capital M. So here we have this one. So first of all, we have the magnetic dipole. What is magnetic dipole? A magnetic dipole consists of two unlike magnetic poles like north pole and south pole. Unlike poles means they are north pole and south pole, north and south poles. Okay, of equal strength, both north pole and south pole having the equal strength, that can be represented by Q. So separated by small distance, that is 2L. What is this distance? It is 2L. So now magnetic dipole consists of two unlike north pole and south pole of equal strength separated by small distance. So that is called magnetic dipole. Okay, so here we learn one factor that is called magnetic dipole moment. So magnetic dipole moment is given by this formula, that is pole strength into magnetic length. Here it is given, no? So pole strength into magnetic length will give you the magnetic, just a minute, yeah. So here we have magnetic dipole moment. It's very important. So Qm into 2L and its unit is ampere meter square. So in moving charges magnetism, or in moving charges magnetism only, we have stated that dipole moment M is given by I into A. Yes or no? So that's why we get ampere for current and meter square for area as the unit. So the unit of magnetic dipole moment is ampere meter square. So try to remember this formula, that is M is equal to Qm into 2L, where Qm is pole strength. Okay, Qm is pole strength. Next, we have a bar magnet as an equivalent solenoid. So here we have a solenoid which is carrying current I. So if you calculate the magnetic field, or if you derive the expression for magnetic field along the axis, you will get this formula, that is magnetic field along the axis of the solenoid is given by, this is the simplified one, mu naught by 4 pi 2m divided by r cube. So this is for solenoid. What if we consider a bar magnet and find the magnetic dipole moment? So if you consider the magnetic field along the axis of the bar magnet, its formula is given by mu naught by 4 pi 2m by r cube. So this is the formula for magnetic field along the axis of dipole or the bar magnet. Look at this, both the formulae are same. That's why we compare solenoid with bar magnet. So current carrying solenoid behaves as a bar magnet. So why? Because this is the reason. Even along the equatorial also you can calculate, they will give the same value of magnetic field. Next we have dipole in uniform magnetic field. If you consider uniform magnetic field here, okay, and let me take a magnetic bar. Here we have a magnetic bar. So here, where is the North Pole? We can consider on either sides. So let me consider the North Pole is this side and South Pole is this side. So we know that the magnetic field lines are directed from north to south. So that's why they experience a force. So like this. So there will be one force acting on North Pole in this direction. So another force acting on South Pole in this direction. So the net force on them will be zero. If the dipole is placed in uniform magnetic field, the net force is F minus F, which is equal to 0. But what about torque? Torque is given by M cross B. Torque is a vector quantity, so M cross B, that is given here, no? Or in scalar form, you can write tau is equal to MB sin theta. If theta is 90 degree, so what will be the torque? And if theta is 0 degree, what will be the torque? If theta is 90 degree, torque is maximum, that is M into B. If theta is 0 degree, torque is minimum, that is 0. Sin 0 is 0. Okay, so then we can derive the expression for potential energy also. The potential energy is given by U, that is equal to, you will get minus MB cos theta, that is equal to minus M dot B. Okay, M dot B. So these two are the formulae for torque acting and potential energy of the dipole. So then we have mentioned the expression for time period of oscillation of small compass needle in a uniform magnetic field. So dear students, let us consider uniform magnetic field here, similar to previous case again. So and keep one magnetic needle in it. So if I keep one magnet needle in it, so there is north pole and south pole in it. So if you pull it to one side and leave, what happens? It oscillates. So it oscillates to and fro direction, or it first comes to right side and then moves to left side. So oscillations will be there. What is the time period of that oscillation? That is given by this formula. T is equal to 2 pi I mb under the root, where I is moment of inertia, not the current. M is dipole moment given by the unit ampere meter square, and B is magnetic field strength in that particular region, and T is the time period. This is very important formula. Then we have the electrostatic analogs. So we can compare electrostatics with electric field with magnetic field. So in case of electric field, we have E. So in case of magnetic field, we have B. They are analogous. Electric field lines, magnetic field lines, electric field, magnetic field. In case of electric field, we have the electric dipole moment, and here in magnetic field we have magnetic dipole moment. There we have constant, that is 1 by 4 pi epsilon. Here we have the constant, so mu naught by 4 pi. All these things are there. We can compare few formulae also. Gauss-Lane magnetism, Gauss-Lane electrostatics, magnetic field along the axis of the dipole, electric field along the axis of the dipole, magnetic field along the equatorial, and here also electric field along the equatorial. So many comparisons are there. So that we can see here also. Look at this. In electrostatics we have the constant 1 by epsilon naught. Here we have mu naught. Epsilon naught is permittivity, mu naught is permeability. Here we have dipole moment P. Here we have dipole moment M. Here we have electric field for the short dipole, which is given by minus P divided by mu naught 4 pi epsilon naught r cube for along the axis, and minus mu naught M divided by 4 pi r cube Okay, so along the axis, along the equatorial, and torque, potential energy, all those things are there. You can compare. So then we have the magnetism and Gauss law. So first of all, you should know what is magnetic flux. So magnetic flux is given by the formula phi is equal to BA cos theta. If I consider an area here, let's consider the magnetic field lines passing through this in this direction. So but area vector is in this direction. So they're making an angle theta with the area vector. So therefore, the magnetic flux is given by number of field lines passing normal to the given area. Number of magnetic field lines passing normal to the given area is given by phi is equal to BA cos theta. Phi is equal to BA cos theta, where B is magnetic field, A is area of cross section. So phi is given by the unit Weber. It's a scalar quantity. Then we have this one, a point, that is magnetic flux over a closed surface is zero. So if you consider a closed surface, whether you consider the magnet outside it or inside it, so the number of magnetic field lines entering is equal to number of magnetic field lines leaving. So wherever the source it may be, so the magnetic field lines, since they form closed loops, so the flux will be zero. The total magnetic flux will be zero over a closed surface. So that is given by this law that is called Gauss law in magnetism. So here we have phi b is equal to closed integral of magnetic field over a surface equal to 0. Correct? No, this is called Gauss law in magnetism. This formula is also important. Then we have some definitions like magnetization, magnetic intensity, all these things. So here magnetization is given by the dipole moment per unit volume. Dipole moment created per unit volume. So that gives you magnetization, how much the material has got magnetized for the applied magnetic field is given by magnetization, and magnetic intensity is given by this. So magnetization is given by M. So magnetic intensity is given by H, that is given by B divided by mu, or B naught divided by mu naught. So how do you define it? It is the degree to which the magnetizing field can magnetize a material. It is the degree to which the magnetizing field can magnetize a material, is known as magnetic intensity, and its unit is ampere per meter. Here also unit is ampere per meter. So try to remember these two formulae. You can note down all these formulae and use them to solve the numerical questions. Then we have permeability. It defines how much magnetic field should be there in a medium. The ability of the substance to allow the magnetic field lines to pass through it is known as magnetic uh, permeability. So magnetic permeability of a substance is equal to the ratio of magnitude of magnetic induction to the um, intensity of magnetic field. So then we have relative magnetic permeability, mu r is equal to B by B naught, and susceptibility is given by M by H. So these are the different formulae. These definitions are very important for your board examination. Chi is the susceptibility, mu r is relative permeability, and mu is permeability of given medium. You can pause the video and write the formulae. Then we have the relation between the magnetic field, magnetic intensity, and magnetization. So the magnetic field B is given by mu naught absolute permeability, magnetic intensity of magnetization M, and magnetic intensity H. So this is the formula that is given here by considering the solenoid as an example. Okay, so then we can derive the relation between susceptibility and relative permeability. So here the final formula is very very important. Mu r is equal to uh, 1 plus chi. We can also write mu is equal to mu naught into 1 plus chi, where chi is susceptibility. See, that is given here. This formula also we use sometimes to uh, I mean in competitive examinations to solve chi or mu. Next we have the magnetic materials. Based on this, there is a law called Curie's law. So diamagnetic materials slightly get repelled by magnet, paramagnetic slightly get attracted by magnet, ferromagnetic strongly get attracted by magnet. So here susceptibility is inversely proportional to temperature. So if you remove the proportionality sign, you'll get a constant called C, called Curie's law. So this is called Curie's law, which is applicable for ferromagnetic as well as paramagnetic materials. But diamagnetic materials are not dependent on temperature. So theory I'm not explaining here, but here I have the list of differences between diamagnetic, paramagnetic, ferromagnetic. You can go through it. So in theory concept, I'll explain all those things again later. So this is the one I have copied it from NCERT textbook as it is. So here we have different factors that you have learned in this chapter, that is permeability of free space. Then we have magnetic field, magnetic moment, magnetic flux, magnetization, intensity of magnetic intensity, and then we have susceptibility, relative permeability, and magnetic permeability of the medium. So whether they are scalars or vectors, the nature is also given here, and there are dimensional formulae which is important for your KCT examinations, and units which are very important for your board examinations, and their values also given here. You can practice these values. So this is about this video. We'll meet you in the next video. Till then, take care. Bye bye.